Hello, Count Sacke here, back with another Genshin Impact video. Today, I will be doing a follow-up to my most recent video, or at least my most recent physics video, remeasuring gravity, where I use statistics to calculate the gravitational acceleration. I'll mainly be focusing on replying or debunking a specific comment I saw in that video. Now, even though I am doing a debunk, I have to tell you guys, do not send hate to the commenter on this one. I think it is a genuine misconception that people can have, and I don't think it's that hard to see why. In addition, I don't think I provided the proper background between all of the three videos that I've made that are relevant to this topic. So I can't blame the person for making this comment. Regardless, if anything, this video will be focusing on replying to that comment and specifically providing proof that there is a gravitational acceleration. So Slacker's comment basically says that there is no gravitational acceleration. It's just pure and consistent velocity. What surprised me most about this comment is that it wasn't just a one-off thing. It seems like there are quite a bit of people who actually agree with this statement. And well, that's what mainly surprised me about it, and that's why I feel like it's necessary to make a video for this, because if there are so many people that actually do genuinely believe this, then I think it's worth actually proving that this is not the case. And again, don't send hate. Side tangent. For me, sending hate to this guy is like being that teacher who says it's okay to ask questions and then says it's not good, why weren't you listening, you suck, that kind of teacher. So yeah, basically I want to debunk this claim, and since a lot of people seem to agree with it, well, yeah, it's worth making a video about. So, out of all my time explaining all of these topics, going through kinematic equations, derivatives, calculus, integrals, differential equations, all the stuff leading up to this video, I noticed I never really bothered to explain the displacement versus time graph, and well, displacement and acceleration don't have a direct relationship with each other, so it can be difficult to see how this lot of dots can actually show, hey, this is acceleration versus something else. Instead, for this video, I want to focus on a more direct, more easily seeable, or at least should be, or whatever the case is. We're going to measure the velocity directly versus time. Why is measuring the velocity more direct than the displacement? Well, the thing is that acceleration, it is defined as the rate of change in velocity. Technically, there should be a bit of an asterisk here, and it's specifically with respect to time. So, if we can measure our velocity, we can actually literally see how it will change. And that's why in this video, what I'm going to do instead of doing a displacement versus time graph, I'm going to plot a velocity versus time graph. So yeah, here we go. Now, the acceleration can be very, very complicated. There can be many types of profiles that you can get. Maybe you can get sinusoidal, you can get cycloidal, you can get something like this. There are many different types of velocity plots that you can get. But if we limit ourselves to just the kinematic equations, which we will have to, given that we're given the claim of the comment, so kinematic equations, we mainly want to focus our attention on a single equation. Again, the kinematic equations is simply solved by from solving this simple differential equation, which is from solving the differential equation that the second derivative of displacement is equal to acceleration. And well, if you really want to, you could also say that the third derivative of displacement is equal to 0. But regardless, the kinematic equation focus on a constant acceleration. So the acceleration is constant. Let me write that to you look nicer. And well, if you solve that differential equation, as I showed in the first video about measuring distances, you'll get an equation that looks something like this, which is you have v is equal to the acceleration times time plus the initial velocity. So you can think of this as like some final velocity and the initial velocity. So this equation might look a little familiar to some of you. If you don't really see it, well, here you go. Y is equal to mx plus b. Don't you think that this looks suspiciously like a straight line? Look at that. So we have velocity is our y, we have acceleration is our slope, our time is our x variable, and our initial velocity is our b. So yeah, if you kind of remember from this equation, if you plotted your yx mx plus b, this height here, this is b. The height here is b, and well, the slope of this line, that is m. That's what our y equals mx plus b says. So we can expect something like that for the velocity. So if we assume that the object is accelerating at a constant rate, so the acceleration is not zero and it's constant, we can expect some plot that might look something like this. Again, it's a straight line, and well, yeah, the slope of this line is our acceleration. And well, over time, we have here, so this one is our initial velocity, this is our final velocity, or velocity at whatever point in time. Whatever the case is, you can definitely see that, hey, it's a straight line, and this is where our acceleration does not equal to 0 meters per second, or seconds squared. So yeah. But what about the case where the velocity, or what about the case where acceleration is 0? Well, if you take a look at this equation, what if we substitute that our acceleration is equal to 0? Well, then we have v is equal to 0 times time plus v naught. V naught. So this term will just go to 0 because 0 times a number is, well, 0. And then we can see here that our velocity just is equal to our initial velocity. So whatever our initial velocity was, let's just say it's this. We'll do it like, we'll just draw it like here. So it will be a complete horizontal straight line. Okay, close enough. So we have a complete straight line. So here we can see our v naught. And this is for a case where our acceleration is equal to 0. And if we were to like say at like 2 seconds, we see that our velocity is like 5 meters per second. We can expect that at maybe 1,000 seconds or whatever, the velocity is still 5 meters per second. And anything between this whole entire thing, you'll always measure 5 meters per second. And for as long as the acceleration is 0, it'll always be that way. 5 meters per second. And that's why it's a straight horizontal line, because, well, you can see here, the velocity is the y-axis, and when you have a constant velocity or a constant y value or something, it will always appear as a horizontal line with respect to the x-axis. So yeah, that's what these equations mean, and that's how you can interpret the velocity equation. So I hope it's actually a lot more clearer, the distinction with the velocity versus time graph. When you start to consider displacement versus time graphs, there are a lot more different variations that can happen. So basically what we're doing is another form of statistics. We have our null hypothesis, and we have our alternative hypothesis. So for this case, I'm going to give the benefit of the doubt. I'm just going to assume that the gravitational acceleration is truly 0 meters per second squared, as is implied that from the comment. So let me go back to the comment. There is no gravitational acceleration, pure and consistent velocity. Let's just assume that is the case. There is also another technical reason why I am assuming the null hypothesis is this. But if we do assume that our gravitational acceleration is just 0, that means we have a very simple equation. We can actually deal with a very simple differential equation, which is that our velocity is, our rate of change of velocity is 0, which will always imply that our velocity is equal to a constant, no matter what. That's a bit of mathematical technicality. So yeah, that it will always imply that directly from the statement. You can never have any other, you cannot get any other expression from this statement. It will always result in this. for the alternative hypothesis, this will be that our gravitational acceleration is not equal to 0 meters per second squared. So, yeah. I hope you can kind of see that the motivation and whatnot and truly understand what I'm trying to explain here. So how exactly are we going to measure this? Well, basically what I'm doing here is that I'm going to be using the, the Leisure Device Twang Bang Bang minigame that you can purchase in the teapot. And well, it's basically, well, the whole Archer minigame where you can shoot the exploding barrels and then you get a treasure chest or whatever. That's what this minigame is. What I'm basically going to do is I'll be using this Twang Bang Bang minigame to measure the amount of time it takes to fall a single meter. So if you notice over here, we have a barrel that is directly located below a hole. Now, that hole is specifically, well, yeah, it's like, you can see that we have the distance here, and if we kind of fall off the side here, we can see that in real time, we'll be able to see how long it travels, it takes to travel a meter. Now, obviously, we would ideally, if we really want to be accurate about this, it should be directly below the hole. So yeah, that's what I tried to set up here. And well, yeah, let me try to explain a bit of the theory behind it. So we have like some sort of hole here, so draw like a little platform. So we have like a little hole, platform, hole, and here. Then we start, this is at some initial height with respect to the ground. So if I do this, this is at some height, some initial height, we'll call it h naught or something, h naught. And well, we'll measure the time it takes to fall. So like over here we fall, let's say this is 1 meter. We can measure the time it takes though. So we'll say measure delta t1, we'll measure the time it takes to fall that 1 meter. Then for this one, we'll say, hey, we'll measure the time again. So delta t2, how long did it take to travel another meter downwards? The total distance here is 2 meters, and well, yeah. And you can see here, yeah, you can travel another meter, and we'll continue to measure the amount of time it took to, fall these increments of 1 meter. So how exactly do we retrieve our velocity versus time graph? Well, that should be pretty simple. All we need to do is to plot our velocity. So maybe we can say that maybe we can say from maybe this distance is t1, and then we plot our velocity, something like that. Plot our velocity, and this one will be, this will be, yeah, we have our velocity, this is our time, and then over here we'll have our delta t2, and we can plot another velocity or something, and maybe here we have like delta t3. Now I'm not spacing these out evenly because it might actually be like that. Who knows what it will be? And well, this will continue on until we collect as many as we have. So we have, and then after that we have delta tn, which it might look something like that. If anything, well, yeah. And then after that we can plot a straight line and see how well it fits the data, and we can will be even able to see, hey, is the acceleration 0 or is it not? Or is it 0 or is it not? If we see that it's like something like this, like it slowly slopes up like this, then we can say that the velocity is not 0. But if we see something that's more akin to something like this, maybe, I don't know, maybe it might even be like something like that. Maybe the plot might do something like this. It might be more debatable about, hey, maybe the acceleration is just 0. But yeah, we'll have to measure the slope for that one. We can use linear regression and we'll be able to see, hey, is the velocity, is it changing or is it not? So yeah, we will expect to see some fluctuations. Now, I think it's worth mentioning that these plots, this is like V1, this is V1, and this is T1. Then this one is V2, T2. Then this one is V3, T3, and so on, all the way up until Vn, Tn. Now, what is the equation for this? So V, whatever it may be, any index, it could be V1, V2, V3, whatever, and so on. The velocity at the ith sample or whatever is going to be equal to 1 meter divided by the amount of time for that interval. So yeah, you can see here V1 is equal to 1 meter divided by the change in so if we were to substitute T1, this will just, or for V1, it will just be this. So if we want to calculate the time that it takes to go to, say, this velocity, well, we have to do is sum up from all of the previous ones. So yeah, I'll just use m or something. M is equal to 1 and sum it up all the way up to the ith one. So we have t divided by tm, and you add up all of them. So if we want T3, well, obviously that's going to be T1 plus T2 plus T3, or actually no, delta T1 plus delta T2 plus delta T3. So that's how you would calculate this thing. That's how we're going to plot this thing. Hopefully I presented enough background so that you can understand the methodology and whatnot. Alright, so here I am. I'm going to record my sample for this data. And well, I think we'll just only do a single set of sample data. It's going to be very messy and it's not going to look that nice, I'll be honest. But I don't think we really should do anything more than that. So yeah, I'll go ahead and get started. So first I'm going to start the game. And well, I'm just going to run into this and start climbing. Now, I have to look straight down so that way I can see the distance, and then I'll let go, and there we go. That's all it is. Hopefully we'll be able to see what's going on, and well, yeah. So here I am in my spreadsheet, and I'll now be setting it up. So first of all, what we need to do is kind of like get our measured data. I'm like, well, yeah. So what we have is a bunch of times measured in frames between 1 meter intervals. So yeah, that's what we need to show our table. That's what we need to, how we need to set up our table. So here we'll say time in frames, and then we'll say time in seconds because we want to convert between the two, and then we can calculate our velocity, which is in meters per second. Now, to convert between times in frames to time in seconds, well, we can make use of a very simple conversion. So if we consider 1 second, or sorry, 1 frame, or whatever, x frames, or whatever, the point is, if we multiply and divide this by, let's say, if we know that our frame rate is like 60, then we know that we have 60 frames per second. Now, due to how this works, you can actually move this per second to the numerator, and what happens is that your frames will actually cancel each other out, and you'll be left with seconds, your time in seconds. So that's what we need to do. We need to put our frame rate. Now, a very quick way to do this is that I'll just put like FPS in frame, like right there, frames per second, and I'll just give it, I'll move it over to the side a bit. Now, here's the thing. We're not, when we do these measurements here, these are delta t, so I think I might as well also indicate this as dt rather than time. So this is going to be dt. dt rather than delta t because we don't have access to delta, or we could if we access the character map, but why not? We'll use character map. And then here I'll search for delta, get it right here, copy, and well, yeah, here we go. We can put delta right there. So then we have delta. Now we'll have t, which is just going to be our time. Well, I'll just put time in seconds. And well, yeah, actually we'll collect our data first, then we'll start implementing our data. One last thing, I think it's worth putting the change in height in meters. In this case, this is just 1. The DH I'm referring to is just the So like these little 1 meters per second, this is specifically DH. That way we know, that's 1 meter. Anyway, enough about that. Let's start measuring. So first I'm going to go into DaVinci Resolve, which is my video editor, and I'll start this. Now I'm going to immediately mute the track. In fact, I can actually just completely get rid of the audio because we don't need to hear my voice for this one. And we'll start measuring. Now, let me just find where I start the thing. So yeah, okay, we're gonna cut out a lot of this, that way we can just much more quickly see it. Downward, and well, yeah. Okay, we'll start it like this. So you see here we have 13, and then we'll start it from 12 rather than 13. So we'll start, whoops, I did a double cut there. So the moment I'll do a cut the moment it turns 12. So I just need to really confirm what the heck is happening here. It's really laggy, I'm sorry. So, okay, on this frame, it turns 12, so I'm gonna make a cut, and I'm going to delete that because we don't need it. Then I'm just gonna go frame by frame until we see that it turns to 11 meters. So let's see. There you go, turns to 11, and on that frame, we'll make a cut. Next, we're gonna zoom in a bit more, and then we can actually measure the frames, which is 13 in this case. So we'll go to our velocity versus time and input 13. And well, I'll just continue repeating this process for the rest of the, repeating this process for the rest of the stuff. So yeah, here we go, 10. All right, so now we've collected all of the delta t's here. So yeah, anyway, so let's go ahead and now calculate the delta t in seconds. So obviously what we mentioned earlier, we take our time in frames and we divide that by our frames per second. We can do that for all of these. Now I'm just gonna reduce the number of sig figs we have here, that way we don't explode our brains. Next, we want to compute is the time in seconds. Now, as we showed earlier, this is this equation over here. So yeah, we have this equation for our time. And well, what we do is we take the sum of this to be 2, and yeah, like that. Then what I'm going to do is specifically lock this first one, that way when I go down here, you can see, hey, it's increased, and that's actually the sum of those two. So yeah, you can see that, and then we can continue this for the rest of the stuff. See here, yeah, sum until there, and so on. And now we have our times. Now to calculate the velocity, remember we take our height, change in height, divided by the change in time. So we'll take that and we'll lock it. I'm pressing F4 to lock it, and then we can divide that by the change of time. And then we can do that for everything. So now we have a bunch of these. You might notice here that the velocity is actually fluctuating quite a lot, or it can fluctuate quite a lot. I'll say that this method right now is not very rigorous, and I would not actually recommend actually using this to measure the acceleration. But I'm just trying to show you, even if it's not, because I'm not trying to give you a precise measurement of acceleration here. What I'm trying to do is show you, hey, the object can accelerate. So I don't need extremely high, like extremely good data. I think that the extremely good data is actually in my previous video, and the better data, even more data, will show up in my next video for when I measure the terminal velocity. So yeah, again, even though this data isn't like the most clean and there's quite a bit of error, you have to keep in mind that what I'm trying to do here is just prove this statement here. I'm just trying to prove this statement. I'm not trying to get a precise value of, or I'm just trying to prove this statement. Actually, well, if we're doing, we're really being proper about this, because we're assuming that we're assuming this to be true. So assumed, to be true. So we're going to assume this is true, and then only when we see the evidence will we reject that notion. So we're assuming that to be true. All right. So yeah, we can now measure our velocity versus time graph and say, hey, we can even take it and plot it on a chart. It might not, yeah, you can see it's not very clean. Again, remember, this is like, what, how many samples is this? Like, it's legit only 12 samples, so give me a break here. Just give me a break here. The data's not that clean, but we're working with what we got. Now, how exactly are we going to, determine the best fit line for all this data points? So, earlier I showed, hey, you can draw a straight line or something between all these data points. So how do we actually determine that? And well, we use something called linear regression. So let me go back to statistics here. This is linear regression. So right here, linear regression. Now, there is also multi-linear regression, but for our case, we're only focusing on linear regression. Now, there are equations for this, and that you can literally very easily determine them. It's like, for example, if we have the equation y is equal to beta times x, or let's say beta 1 times x plus beta naught. You can kind of see the y equals mx plus b here, so y equals mx plus b. We're just basically we're finding the best possible straight line that we can fit, and we know for sure that this is going to be a straight line because we're using kinematics, and well, we have a constant. We're assuming that the gravitational acceleration is constant, so we can in fact use linear regression here. Now, so yeah, here we can very easily calculate for beta. We can actually calculate beta with something I think that's the equation for it. But yeah, I personally don't like memorizing these equations. I barely even remember them myself. What I like to do is something much more mainstream, and it could actually even be applied to any number of variables. For our case, we're only considering where y is a function of a single variable, but there could also be maybe u, there could be v, w, there could be z, and many more variables that this thing is a function of, as long as it's linear. But for me, I like using this method, which it's kind of similar to what I showed in the video, where you have it uses a matrix and linear algebra. So we have our I think you might, if you've seen the previous video, some of the stuff might look a little familiar. And the gist is, you can actually use the least squares method, and from that, you'll obtain equations that look very similar to whatever the heck I calculated last time. So from the least squares method, you'll obtain that the best possible estimator for beta is actually specifically equal to this. So we have x transpose, then times the matrix X, and you multiply that, and that's inverted. And then we take this X transpose times the Y samples, and then of course the best estimator for Y is specifically X multiplied by the best estimators for this. So let me just, again, there you go. So yeah, you'll get these two equations, and they should look pretty familiar, same exact form, except, I had vectors instead, yeah. You'll get the same exact equations. Now, obviously, these equations kind of don't really look like anything and could probably confuse a lot of people. So yeah, what I like about this equations is that, well, it's actually very easy to calculate them. If you know anything about linear algebra, you know how to take a transpose. Now, the transpose is if you imagine taking, if you just invert it you swapped index, like this is the 1 1 index, and then this one's like the 1 2 index. In this case, like the 1 2 index, you imagine like you take this one and put it into the 2 1 index. So we just swap it like this. We swap them around, and whatever, you can find out how to do the transpose on your own. So you can see here x like this. You can find our matrix like this, and then our matrix ends up becoming sideways. You can see here we have x1 here, and now we have x2, and our xn is now like that. So it's now sideways. It's basically, we kind of flipped it on its head. And we can very easily calculate this. So now I'm probably not doing a good job at explaining why I like this method a lot more, but the main thing about this is that it can generalize to any number of things. Now we can actually, because matrix multiplication is associative, we can actually multiply x transpose and y. There you go. That's what this is. Now, this equation is actually very nice. You could very easily calculate that. You can actually calculate this. It doesn't take that long to calculate. Well, granted, this thing might take a while to calculate depending on how big your matrix is, and well, it might be better if it's really large. It might just be better to use, a computer or something. But yeah. Anyway, enough about that. We can actually calculate this. We can actually calculate the inverse of this. Now, this is going to sound like a bunch of jargon, and I apologize, but if we want to calculate the inverse of a matrix, let's say A, what we do is we find the adjoint matrix of A, and then you divide that by the determinant of A. Now, again, this might just sound like a bunch of mathematical jargon, and I apologize. It's just a bunch of math. It really is just a bunch of math jargon, and then the adjoint of matrix A is also equal to the cofactor matrix to the transpose of the cofactor matrix of A. So yeah, this is definitely a very ugly. At least it looks very ugly. If I won't deny, it's a lot of math. But what's so nice about it is that this matrix here, you can very easily expand it a lot. You can very easily expand it. So like you can see here that we have the sum of x, and then if you were to expand this, it actually becomes like this: sum of x squared. Sum of x squared is going to be sum of x. Then we have sum of x squared. Then you can do this is sum of x cubed, and then sum of. You don't even need to go through this entire thing of multiplying your matrices over and over. You can keep on expanding this for as many variables that are present in your thing. So that's why I really like this method, and that's why I calculate linear regression or whatever using this method, because it can expand to any number of parameters in this case. Yeah, I could go on. It'll go on and on and on and on. So yeah. Anyway. So actually, I mentioned a bunch of math jargon. I'm sorry, but I'll go ahead and now calculate these values. We can do that very easily. See, first off we need to compute n. I'm going to go open up my character map here, and I'm going to reset. I'm going to look for sigma, because that's the summation symbol. So for this, all we need to calculate, there are only a few things that we need to calculate. We need to calculate this, and that. So yeah, let's calculate. So we have sigma, our sum of x, then we have sum of x, we'll do x squared like that. Then we'll have sum of sum of y, and then we'll have sum of x times y. So we just need to compute all of these, and then we'll be able to obtain our matrices and whatnot. So this one, we simply just need to perform a count function of this. We have 12 samples here. Is that right? That should be, yeah, I think that's right. So yeah, we have 12 samples. All right, so then after we can sum up our values, so we have sum of x, which is this one here. Then we have sum of x squared. So I'm using the sum product here, c2 times c, c2 times c. There we go. Sum product. Then we can now calculate the sum of our y term, so this. Then we have to do a sum product of c2 times c, and then we multiply that with d2 times d. There we go. And now we can calculate for our x transpose, which can also be x prime. And then, well, it's simply just this matrix. Not too difficult to calculate. It's literally just this matrix. Now to invert it, we actually need to find the cofactor matrix. So our cofactor matrix, well, if you want to be technical, you just take, if you get the determinant of whatever is, yeah, okay, this is really awkward. Whatever the case is, in a 2x2 matrix, it's very simple. It's actually a very simple here. And then if we want to get the adjoint matrix of that, well, you just take the transpose of it. And what's nice about this, because it's a symmetrical matrix, it's exactly equal to itself. So there we go, transpose. Then if we want to calculate the determinant of the matrix, well, we can very easily just take our cofactor matrix, and we'll do we can very easily do this sum product of this, and then we take the sum product with that. And there we go, you have our determinant. If you want to do it the old-fashioned way, you can. If you want to do it this way, like this, then minus that times that, same exact value, you get the point. There we go, we have our determinant, and now we can easily determine the inverse matrix of that by doing, we take our adjoint, let me go over there, adjoint matrix, this one divided by the determinant, like so. There you go, and now we can very easily prime, we have x prime times y, and that's simply going to be equal to this, and then we take that. Next, I'm just going to do this for computation purposes only. So what I'm going to do is just take the transpose of this, that way it's easy to do the product. So then we can calculate our B1, B0, and B0. So we'll do sum product, this, and then this, and then we can easily do sum product of this and this. And these are our values. Now, I'll go ahead and plot these values. Let me move stuff around here, that way we have more space. So, predicted velocity in meters per second. So this is pretty easy to do. We take our B1, I'm going to lock that in place, multiply it by our time, and add it with beta naught. And we're going to lock that one in place, and we can do that for all of these values. Then what we can do, I'm going to include it in our plot right here. So add our velocity. Let's add a new, or yeah, let's add something new. Let's add another range. This one right there, velocity, predicted velocity. Yeah, you can see it now. I'm going to go for a line chart here, just to show it a lot more clearly. I'll fix this one here. So line thickness, I'll set this to 0, and I'll make the point size 7. That way you can see it. I'll make it even 10. I'll even make it 10. And yeah, you can kind of see here, this line, no matter what, you can kind of just see it. It really is just it is increasing. There is a slope to this line. Well, what does that mean? As we discussed earlier, a non-zero slope means the acceleration is not equal to 0. And well, if that is truly the case, then we can actually conclude that, hey, the gravitational acceleration is not equal to 0. There is a gravitational acceleration. And well, I hope that this can actually prove that. This is a long video, and honestly, yeah, it really is a lot. Now, if you're wondering, there's also another pretty easy way to do this. There's a faster way to do this. I just like to show the long way because I like to actually explain things. So if I actually delete that for a second here and I go to my series, go to my velocity, then I put a trend line, and then I just decide to show the equation. Well, it's the same exact, it's literally the same exact values here. So yeah, there we go. And something else we can do is also calculate the r squared. I could calculate the r squared, and it agrees with about 79% of the data. It's not the best fit because it's kind of, there's a lot of error. So I would expect I wouldn't expect the extreme accuracy that I got with the other method. So yeah. Regardless, I do think that this is a pretty interesting method, and it does seem quite useful. But yeah, that's really about it for now. So thanks for watching and hope you've enjoyed.